Hello everyone, this is Mona, Sama, and Farida, and today we're going to present our project. This is the table of contents. Our problem is about brain tumor segmentation. We're using MRI scans to detect whether or not there is a tumor in the brain. Our dataset has 369 brain images. Each patient has 155 slices and 4 channels. This is a visualization of one patient having 155 slices, and this is the 4 channels compared to the ground truth.
Okay, so for our chosen model, we had the two-path CNN, which is a cascading architecture where you had two inputs taken from the image, and these inputs are assembled after several activation functions. And then the output of the model will be, the first model will be the input of the next one, and the final output would be the prediction of whether there's a brain tumor or not. After that, we evaluated our models using six performance metrics, which are the die-score, which is the degree of overlap between the prediction and the ground truth, where 0 is no overlap and 1 is perfect overlap. And then sensitivity or recall, which is how well the model identifies the true positives. Then the accuracy and the F1 score, which is a combination of the recall and the precision. And finally, we have the loss and the precision. After that, for our implementation, we did pre-processing the baseline model, and then we did it with 2 attention gates, and then the unit and the ensemble of the 2 models. For our pre-processing, we had a few methods where we either limited the slices and channels, or the slices only, or the patients only, and we finally chose to limit the patients because the other results led to overfitting, and these are our graphs that show overfitting.
Moving on to the skull stripping, which is also known as the brain extraction. It removes non-brain areas before normalizing the brain, and it's useful for anonymizing brain scans, and it's helpful to improve the model's robustness. We've also did the canny and controlled edge detection, which detects abrupt local changes in the intensity of the image and smooths the image to eliminate noise, and then it finds the image gradient. And as you can see, the output is the cropped image without the unnecessary pixels.
After that, our baseline model, we did the classic 80-20 training testing split, and we did the ReLU and the sigmoid activation functions in our dense layers, and we included same planning and batch normalization for a more effective analysis, and lastly, we optimized using Adam. This is the model summary, and as you can see, most of our parameters are trainable, so the model is more customized to our data. These are our results for the two-path CNN, where you can see the accuracy is somewhere around 83%. The model loss approaches 0. The recall is around 80%, and so is the precision. And now to improve our model even further, we added attention gates to the two-path CNN by focusing on different regions of the image. This is the model summary, and as you can see, the trainable parameters are the majority of the total parameters. These are our results, where the accuracy improved to be somewhere between 90 and 95%. The model loss approached 0 as well, and the precision and recall are around 90%. And the same thing can be said for the F1 score and the die-score.
Moving on to our second model, which is the unit. It's basically a CNN specifically designed for biomedical image segmentation, and it's effective for segmenting regions of interest that are small and have complex shapes. It was introduced in 2015, and as you can see in its architecture, it has a downsampling path where the number of layers decrease as you go, a convolutional layer, and finally an upsampling layer where the number of layers increase as you go. However, one of the challenges was that unit was based on pixel-wise segmentation, but we adjusted it to depend on the image-wise segmentation since we didn't have the pixel labels. Here's the model summary, and as you can see as well, most of the parameters are trainable. For the accuracy, it was the constant across all epochs, reaching 33%. For the loss, it was fluctuating, but at the end, it reached 0.5. The model recall was almost 1. The precision was between 0.47 and 0.48. The F1 score was between 0.64 and 0.65, and the dice was also between 0.64 and 0.65.
Then we implemented ensemble of two-path and the unit models to capture the best of both worlds. Ensemble helps us in better generalizing the model and having less overfitting. And we did 2 trials of ensemble, one using simple averaging and then another one by averaging the predictions and then stacking through ADA boost. And these are the results of the simple averaging and the stacking using ADA boost.
So this is our live demo. We start by loading our model. This is the two-path CNN. And then we construct a table to compare the results. And then here we load a random patient, and this is the visualization for it. After that, we run the pre-processing of the original data, so it matches the input from before. After that, we run our two-path CNN model, and as you can see here, these are our results, and then we append it to our table. After that, we do the same for the unit. I'm just gonna skim through because takes a while. And these are the results for it. After that, the ensemble with the simple averaging. These are the results, and we append them once again. And lastly, for the ensemble with the ADA boost. These are the final results. And this is the appended table. As you can see here, we compare each model with the accuracy and its prediction compared to the ground truth as well. And the majority predicted correctly, except for the unit on its own.
Moving on to the conclusion to sum everything up, we did skull stripping, pre-processing, mini batch with a batch size 16, two-path CNN. We added attention gates. We tried unit ensemble. We did an ensemble with a simple averaging and ADA boost. For future work, we're considering trying different models, enhancing the two-path CNN in other models, methods, and trying ensemble with different models. Here's the timeline and progress, and here's the team contribution. That's it. Thank you.